All right. So today I would like to talk about circuit analysis in the frequency domain, which I believe will largely be a review of what you guys covered in Circuits 1. So Thursday's lecture was a video recording of an introduction to phasors, impedance, and admittance, and I don't remember whether the video ended with some frequency domain circuit analysis or not. So we're just going to jump into solving maybe a couple of problems here. So let's say that we have the following circuit. I'm going to call this voltage source Vs of t. I'll define what that is in a moment. Call this guy Is of t, 5 ohm resistor, a 2 Henry inductor, and a 0.2 farad capacitor, like so. And our goal will be to figure out our capacitor current, which I'm going to call IC of t, given that Vs of t is equal to 10 cosine 2t plus 15 degrees volts, and Is of t is equal to 2 cosine 2t minus 30 degrees amperes. So hopefully in my last live lecture, I convinced you guys that working a problem like this in the time domain is an absolutely terrible idea. So instead, we're going to analyze this problem in the frequency domain. And in order to do that, we need to complete a couple of initial steps. So our first step is to convert all voltages and currents into the frequency domain, or effectively replace our voltages and currents with phasors. So if I redraw my circuit here, what would the phasor representation of my voltage Vs of t be? So how do we convert from the time domain directly to the frequency domain or phasor domain?
The amplitude and the angle that is added.
Exactly right. So all we need, the only two pieces of information that we need to include are the amplitude of the waveform and the phase angle of the waveform. So for our voltage, what would be its phasor representation?
10 phase angle 15
Yeah,
degrees.
10 angle 15 degrees. Volts. All right, and our current would then be 2 angle negative 30. Great. For this particular problem, I gave you both things as a cosine function, so there was no need to convert. But if I had, say, made our current IS as 2 sine 2t minus 30 degrees, we would have had to convert that sine to a cosine first, and then gotten the phasor representation from that. All right, so our second step is going to be to convert all of our resistances, capacitances, and inductances to impedances. So the impedance of a resistor, I'll call it ZR, is just given as the resistor value itself. So in this case, that would simply be 5 ohms. So the value of the resistor does not change. The impedance of our capacitor, ZC, is going to be 1 over J times omega. So what's omega? Where do we find that out? Exactly right. So omega is the angular frequency, which is the operator that is acting on time, or t, inside that cosine function. So in this case, we have an omega of 2 radians per second. And finally, we put in our capacitor value, which is 0.2 farads, where a farad is a amp second per volt. And so we have per seconds multiplied by seconds. So this is going to look like 1 over J times 0.4 amps per volt, which, if my math is correct, will look like negative J 2.5 ohms. Let me just double check that real quick. 1 over 0.4, 2.5, yep. So our capacitor, negative J 2.5 ohms. And finally, excuse me, converting our inductance, that is J times omega times L, where a Henry is a volt second per amp. So the per seconds cancels the seconds. We have 2 times 2, so that looks like J 4 ohms. And our quantity of interest, I will list as a phasor current IC, where I'm denoting that it's a phasor by the bar over the top. So we have completely converted our signal from the time domain into the frequency domain, and now we can apply simple DC circuit analysis techniques involving complex numbers in order to solve for our quantity. So step 3 is use applicable DC analysis. So we can literally use any circuit analysis techniques that we want to in order to solve for this thing. So if this were a DC circuit, what would be the most efficient means by which to solve for this quantity IC? So we could combine those two impedances together to make a single impedance, okay? What would we do after that? Okay. So a source transformation on the current source and the resistor can't happen because the resistor isn't parallel with the current source. So we could do that, but once you change the layout of the circuit like that, I would argue that you no longer know what that IC represents, right? So we want to combining the inductor and the capacitor together will be okay because the conductor and the inductor and the capacitor share the same current because they're connected in series. But once we do a transformation involving that equivalent impedance, then we're getting into areas where we're not guaranteed that the results of our analysis will be correct. So we could do mesh analysis. We could also do superposition. So let me talk about mesh analysis first. There is absolutely nothing wrong with doing mesh analysis for this problem. I feel like it might be a little bit overkill, but that's not that big of a deal. My biggest concern with mesh analysis is that because it's using complex numbers, it would require the use of a computer to solve. I guess technically we could do it using Cramer's rule by hand, but I don't want to because Cramer's rule with complex numbers gets really ugly and it's just ripe for us making a mistake. Superposition would absolutely work here. We'd have to solve the circuit twice, but it'll be pretty trivial. Another potential thing that we could do would be do a source transformation on the practical voltage source on the left-hand side. And then we could combine those current sources because they'll be in parallel and then use current division. But to me, the easiest way here would be applying the principles of superposition. Because I can look at this guy and see that I'm just going to do Ohm's law with the voltage source on and the current source off, and current division with the current source on and the voltage source off, and then add the results together. So those are two pretty simple steps, right? So mesh will absolutely work, but I don't want to pull out MathCAD, so I'm not going to do it. So let's use superposition. So with the voltage source on and the current source off, our circuit looks like this. So we'd have 10 angle 15 degrees volts. Our 5 ohm resistor. Our J4 ohm inductor. Our minus J 2.5 ohm capacitor. And recall that since we are turning the current source off, we just replace it with an open circuit or we pluck it out of the circuit entirely. I'm going to call this current IC prime. And it should be fairly trivial to see now that we can figure out what IC prime is just using Ohm's law, right? So IC prime, would be 10 angle 15 degrees volts divided by 5 ohms plus J4 ohms minus J 2.5 ohms. which I get to be 1.916 with an angle of negative 1.7. 1.699 degrees. Yes. Change the mode on my calculator real quick to give me my answers in polar form. So I don't particularly mind if you choose to express stuff in rectangular form or polar form unless I explicitly tell you to do one or the other. But I'm much more comfortable working with polar form complex numbers. So that's how I typically tend to express my answers. And we'll see in a minute when we have to convert back to the time domain that the polar form complex number gives us the easiest path with which to do that. So before we move on, any questions regarding this circuit analysis or the answer I got? Hopefully applying Ohm's law at this stage in your electrical engineering careers is fairly straightforward. So now we'll analyze this guy with the voltage source off and the current source on. So to turn off our voltage source, we replace it with a short circuit. We have our 5 ohm resistor. Our current source is on, and it has a value of 2 angle negative 30. Negative J 2.5 ohms. This will be IC double prime. And as I mentioned previously, I believe that current division would be the easiest means by which to determine this particular value for IC double prime. So applying current division, we would have IC double prime as 2 angle negative 30 degrees amps. And in my numerator, I'm going to have the impedance of the branch that I'm in, or excuse me, the reciprocal of the impedance of the branch that I'm interested in. So in this case, that would look like 1 over J4 ohm minus J 2.5 ohms. So I have to look at that whole branch, not just the capacitor impedance by itself, because that current flows through that equivalent series impedance. In my denominator, I have the reciprocals of each of the branches. So that would be, oops, goodness, 1 over 5 ohms plus 1 over J4 minus J 2.5. Close my brackets here, and I can throw this directly into my calculator. And I get 1.916 with an angle of negative 46 0.699 degrees. Oops, let me double check that. Unless that's what either of you guys got. Yep, okay. Sorry, I was concerned purely because I get the exact same result off for both the top and the bottom, but there's a phase angle difference of 45 degrees. That's just because of the numbers that I chose. I just wanted to make sure I wasn't doing something goofy. All right, so using the additivity principle of superposition, that we can say that with the voltage source on and the current source on, IC phasor is simply IC prime plus IC double prime, which I get to be 3.54 with an angle of negative 24.199 degrees amps. So our last step here is to convert our results back to the time domain. So IC of t will be what? How do we convert from the frequency domain to the time domain?
So the inverse, so we take the amplitude 3.5.
Okay, so the amplitude 3.540 cosine. Okay, so 2t phase angle, yeah. So negative 24.199 degrees amps. And there we have it. We've solved our circuit using simple DC circuit analysis techniques, one of a multitude of different ways that we could have done it. But we did not have to involve any terrifying calculus and or trig identities to get there. All right, so there is something else that I want to talk about today. It won't take particularly long. So I guess I want to ask you guys, how much practice do you need employing DC circuit analysis techniques to circuits in the frequency domain?
Say, solid 5 out of 10.
You're at a 5 out of 10. So what do you feel, what techniques do you feel that you're the least comfortable with?
When it comes to AC analysis,
Sure.
I would say mesh would be really hard sometimes.
Okay.
I think the main difficulty here is working with the calculations for rectangular formats and polar formats.
Right. So, okay. So,
Just mapping.
All right. So let's set up this exact same problem, but solve it using mesh then, since you said specifically mesh might be an issue. And let me go ahead and get MathCAD pulling up in the background. So this is going to be step 3. I'm going to put a star by it because we're doing the same thing, but in a different way. All right, so we have 10 angle positive 15 degrees volts goes here. 5 ohms goes here. 2 angle negative 30 degrees amps goes here. J 4 ohms goes here. And negative J 2.5 ohms goes here. Here is our quantity of interest, IC. So using mesh means I need to identify my mesh currents. So I'm going to have a mesh current here, which I'm going to call I1. And I'll have a mesh current around this guy, which I will call I2. Since I have an interior current source, I'm going to have to apply the super mesh technique, which means I'm going to have to write a Kirchhoff's voltage law equation around the perimeter of the circuit. So let's go ahead and do that. So this would be KVL at super mesh 1 and 2. So starting at the bottom left-hand corner, we see the negative polarity terminal of our voltage source first. So, sorry, negative 10 angle 15 degrees volts plus 5 ohms times mesh current I1 plus J4 ohms times mesh current I2 plus negative J 2.5 ohms times mesh current I2 is equal to 0. So writing our mesh equation is exactly the same as previous. We just have J's and negative J's whenever we have inductors and capacitors respectively. When I'm setting up these equations, use a lot of parentheses, as you can see, just trying to make things consistent. So if I'm given something as a negative number, I add it as a negative number so that when I get into my computer algebra tool, I don't make silly mistakes from having done conversions and stuff like that. So that's one equation. Where's our second equation going to come from? Yeah, so anytime we have a current source and we're doing mesh analysis, we should have a current relationship equation to deal with as well. So our current relationship equation here is going to be 2 angle negative 30 degrees amps equal to what?
Oh yeah, I1 minus I2.
I disagree.
Oh, that's negative, right? That's going up. I2 minus
I2 minus I1, right. So it's I2 minus I1 because as I2 flows around its clockwise path, it is flowing in this direction through the current source, which is in the same direction as indicated by the current source. And as I1 flows along its clockwise path, it's flowing in the opposite direction. So it's always the current in the same direction minus the current in the opposite direction. So there we have our two equations, two unknowns, and as I said previously, our calculators are incapable of doing it, and solving these guys by hands is just ripe for simple mathematical errors. So let's use MathCAD. All right, so to set up a system of equations, we're going to use our solve block. So we have two variables, I1, and I typically like to guess 1 angle 0 degrees. So let me explain exactly what I did there, since you guys may not be aware. If we go up here to operators, we can see under the engineering bit, that's how we get our polar angle thing. But there's also a keyboard shortcut, which is Control-Shift-P. So I have remembered that from teaching this class so many times. So I'm just going to hit Control-Shift-P to get that. Now, if we move our mouse over here to the left, we can see that there is a character that is just the degree symbol as well. However, there is no keyboard shortcut, but MathCAD interprets the letters DEG as a unit of degrees. So I'm just going to type that in. One thing that I'm going to have to do here, I always work with the correct units and stuff like that. So I'm going to implicitly multiply. So that means I'm not just going to type A out to the side. I'm going to multiply it by a unit of an amp. The reason why I do implicit multiplication like this is because sometimes MathCAD will interpret things in parentheses as a function of something else operating on it. And I want to make sure that that isn't happening. So in order to do that, I have to actually multiply every time I do this. So there's I1, I2 will set up in the same way. 1 angle 0 degrees amps. All right, so for our constraint equations, we are just going to have those two equations that we wrote. So that was, sorry, negative 10 angle 15 degrees volts plus 5 ohms. So I get the ohm symbol by having uppercase W and then pressing Control G to convert it to its Greek counterpart. So lowercase w, Control G gives you omega. Uppercase W, Control G gives you the ohm symbol, or uppercase omega. Multiply this by our variable I1. Then we have, let's see. Yeah, so MathCAD won't interpret it correctly if you do J4. You would have to do 1J times 4 because it treats J as if it were a unit. MathCAD can use I or J as the imaginary operator, but it needs to be trailing instead of leading, which is leading is the convention that I was taught back in school, but trailing is the one that MathCAD uses. So that's the one that I'm going to do. And I'm going to implicitly multiply this guy by the unit of ohms. Then I multiply by our phasor current of I2. And finally, I'm going to have negative 2.5 J multiplied by my current I2. And all of this is 0. Because I'm using a solve block, I have to, in my constraint equations, use the control equal sign operator, where I use the colon equal sign operator to declare my guesses. My second equation is 2 angle negative 30 degrees amps. Control equals I2 minus I1. And I like to store my answers in a matrix. And the reason I do this is because if I have to do extra mathematical manipulation afterwards, I can. So I'll show you what I mean by that in a second. So I'm going to say I1, I2, colon equals sign, find I1, I2, equal sign. I get two numbers, two complex numbers in rectangular form. To convert them to polar form, which is what we're used to, I go to math formatting. And down here, I can change the different types of complex variables that I get. So for instance, this topmost option is giving me rectangular form with I as the imaginary operator. This next one down is rectangular form with J as the imaginary operator. Then we have this guy right here, which is polar form with our angle in pi radians. Then we have polar form with our angle in radians. And finally, we have polar form with our angle in degrees, which is what we use. So we can see that we get 1.563 angle negative 16.769 degrees amps for I1 and 3.54 angle negative 24.199 degrees for I2. So let's circle back around real quick. How does I2, or how does the mesh currents I1 and I2 relate to our quantity of interest, which is IC? Yeah, IC is exactly the same as mesh current I2. So that was 3.54 with an angle of negative 24.199, which exactly agrees with our previous methodology of solving this circuit. And then obviously all the other steps would be the exact same because it's the exact same circuit. So just as a quick heads up, I could do mathematical manipulations here. None of these will make any sense whatsoever, but I could say I1 plus I2 and I get some answer. What I'm trying to show you is that if I don't do this matrix thing here, so if I just do the find thing, it's not storing those variables. So outside of my solve block, I don't have access to any of that information. So using that matrix to save your variables to be used elsewhere is going to save you a lot of trouble if you wind up using MathCAD to do complex analysis and or when you're working on your power problems and stuff like that, which is going to be one of the next topics that we get into, where you're going to be multiplying phasor voltages times the conjugates of phasor currents and all that kind of good stuff. Being able to store those variables instead of having to explicitly write them out and introduce rounding errors constantly is going to be, I think, a huge benefit to you guys. All right, so was that helpful?
Yep.
All right, so I'm going to work another problem now that's going to look extremely similar. But it's going to throw a wrench into the mix. So, this is 3 Henries. Oh, let's see. Let's make this 10 ohms, and let's make this 1/2 of a farad. Let's say that IS of t is 1 cosine 2t plus 10 degrees. And let's say that Vs of t is 12 sine 3t plus 30 degrees. So we have a circuit here that is being excited at 2 different frequencies, right? So there are 2 sinusoidal forcing functions, but they are both acting at different frequencies. So if we try to analyze this circuit in the way that we analyzed the last one, we'd run into a little bit of an issue in as much as our capacitor and our inductor would have 2 different impedances that we would need to account for. So are there any thoughts on how we might approach a problem like this, being excited at 2 different frequencies? So how would you go about converting a 2 radian per second frequency excitation function into a 3? Like once you change its frequency, it's an entirely different animal, right? So the short answer here is that we're going to have to use superposition, analyzing the circuit 1 frequency at a time, and then adding our results together, right? Because we don't know of a way to combine, say, let's say that we had a voltage, this has nothing to do with this circuit, but let's say that we had a voltage Vx of t was 10 cosine 5t plus 15 cosine 10t. How could we combine them? The short answer is we can't, right? So that's why we have to use superposition here, but we have to be very careful with our application of superposition as well. All right, so with our current source on and our voltage source off, we need to convert this time domain circuit into the frequency domain where we are using the frequency of the current source as omega, right? So our current source is on. So this is going to look like 1 angle 10 degrees. What is our 3 Henry inductor going to look like? Oh, and I guess I should specify what we're looking for here. Yeah, that'll work. So what is our inductor going to look like as an impedance? Yeah, so J times omega, so J times 2 times 3 is J 6 ohms. Our voltage source is off, so we have a short circuit there. The impedance of our resistor does not change, it's just the resistor value itself. What is our capacitor going to look like? Okay, so 1 over, so let's see, so J is times omega. So J times 2 times 1/2 is going to look like J1. So 1 over J1 is just negative J1 ohm. Here is our phasor quantity of interest. I'm going to call it VL prime. How do we solve for it? Right, because we know that the 10 ohm resistor and the negative J1 ohm capacitor are shorted out. So 1 angle 10 times J6 is going to look like 6 angle 100. All right, so that analysis was pretty straightforward. Now let's do current source off and the voltage source on. So my current source off, it's going to be an open circuit. My voltage source here is going to look like, gosh, let's see, 12 angle 30. What is my inductor going to behave like here? So omega in this case is 3 radians per second. So if the frequency went up by 50%, the impedance should go up by 50%. So J 9 ohms. Here's my 10 ohm resistor. Here's my capacitor, which should look like J 2/3 ohms. I think 3/2, yeah, so 2/3. Yep. So what is VL double prime? Pardon? Explain why you think there is no voltage drop over the inductor.
Oh,
Because there's no current flowing through it. That's absolutely correct. 0 volts by inspection, okay? So from this, so I've made a small mistake here in as much as when I glanced at this, I didn't think about how the voltage drop over the inductor with the voltage source on and current source off was going to be 0 because I want to illustrate something. So let's pretend that VL double prime was 2 angle 40 degrees volts, okay? Purely to explain something here. So in the previous example, we used superposition when we first solved it, and we were able to add our phasor currents together to get our result, right? We absolutely cannot do that here because our phasors do not contain our frequency information, right? That information is explicitly suppressed. That's what makes the math significantly easier, is that we don't have to worry about carrying the frequency around and all that kind of good stuff here. But when we have a multi-frequency circuit, it would be very easy for us to say, okay, we're used to doing superposition, and at the end, we just add the results together. But we have to acknowledge that the results are occurring at different frequencies here. So really how this thing looks, we would have VL of T is going to be 6 cosine. I realize I made a mistake here. It doesn't particularly matter. So sine, I have a sine instead of a cosine, so that voltage should be negative 60 degrees. Didn't change the results of our second step at all, but so this should be 6 cosine 2t plus 100 degrees plus 0 cosine 3t plus 0 degrees volts. Or if we had used our pretend value, 2 cosine 3t plus 40 degrees. We cannot add them together in the frequency domain because they are representing answers at different frequencies, okay? Very, very common mistake, which is why I'm trying to browbeat you into remembering it. All right, so we did some frequency domain circuit analysis using simple DC techniques like superposition, Ohm's law, voltage division, all that kind of, or no, we didn't use voltage division, current division, excuse me. We also did some mesh analysis, and I showed you guys how to use and set up a solve block using complex numbers. But we worked a multi-frequency circuit. I think I covered it well enough for you to understand what the steps and all that kind of stuff are and the pitfalls of it. So what else do you want to talk about for today before we get into power tomorrow morning? Anything that you feel you need review on? This multi-frequency stuff is the only thing that is remotely new from what you guys covered in circuits 1.
So we just add them, we just do like this, right?
Yeah, just you have to use if you have a multi-frequency circuit, you have to start using superposition. And then you can use whatever circuit analysis techniques float your boat for each frequency. In this case, I drew the circuit easy enough to where we could just use Ohm's law and inspection. All right, so if you guys don't have anything else for me, then we will start with instantaneous and average power tomorrow, which will largely be a review of circuits 1 stuff. And if we have time, I'll talk about the maximum average power transfer theorem, which will be new to you guys. If we don't talk about it tomorrow, we'll talk about it on Thursday. All right. See you guys tomorrow.